Good day, ladies and gentlemen. My name is Francois Perraud. I'm Product Marketing Manager with Littelfuse. Today we are going to discuss a package that helps fully exploit the advantages of SiC MOSFET and that bridges the gap between standard discrete and power modules. So let's quickly frame the challenge. Let's imagine the management, the customer, and the marketing team have decided that the next-gen design is going to be high power, have a much better efficiency in a much smaller housing. At the same time, there is demand to streamline the PCB design in order to reduce the mounting cost and improve the automation of the production. And you have been assigned as the lead designer. So higher power density, higher efficiency. I hope it's clear to everybody in the audience today. That's a clear case for wide bandgap and SiC. Compact design, simplified mounting. Let's have a look at surface mount components. Then easy peasy, problem solved. Well, not so fast. Maybe we have not considered all the questions. Maybe the thermal performance of standard SMT discrete is not going to suffice, especially if we consider the resistance junction to heatsink or junction to coolant. Then we might need a way to further increase the power density of the initial design because finally we do not have enough space on the PCB. And then I also want to make sure I get the highest performance out of the chip because SiC is really expensive. So do we have a way to solve these extra challenges? Well, enter the SMPD. SMPD stands for Surface Mount Power Device. It's a fully isolated package based on DCP substrate. It's roughly in the size of a €2 coin, as you can see left-hand side. And we have this package since 2012 in mass production, so it's field proven since quite a long time already. The SMPD provides 2.5 kilovolt RMS isolation, UL rated. The thermal performance is excellent, and most importantly, it's pick and place compatible. In a SMPD, one can accommodate a large variety of basic power building blocks, for example, a bridge leg or a booster leg or a one-phase rectifier bridge. And obviously, our topic today is SiC, but this package is available for a variety of technologies such as silicon MOSFETs, IGBTs, diodes, etc., from 40 volt to 3000 volts, or a combination of these devices. Let's review the advantages resulting from integrating chips in a SMPD. We have sufficient pins to provide can-field source connection, thus providing better gate control. The common source inductance is excluded from the gate loops, thus allowing faster switching, reducing the gate oscillations. There is no negative feedback of the load current into the gate loop either, improving the AMI and reducing the risk of parasitic turn-on. So all these features being obviously very important in the context of switching wide bandgap devices. The mutual parasitic inductance is minimized as well as the coupling capacitance to the heatsink. This again improves the EMI, especially the radiated EMI. And overall, the losses of the solutions are minimized. We have a better efficiency of the system. We can operate at lower junction temperatures, simplify the thermal design. We can, of course, expect also advantages at the layout level. So if we compare, for example, here on the left-hand side, the power loop of a design based on TO247, and on the right-hand side with a design based on SMPD, we see that in the case of the SMPD, the power loop is shorter. This means a reduced stray inductance. This means reduced ringings on overshoots, and here as well, an improved safety margin for the design and an improved efficiency. Now, can we observe the advantage we just discussed in reality? To reply to this question, we organized a small benchmark comparing silicon carbide MOSFETs half bridge in SMPD with the same MOSFET in a TO247 3 leads and a similar spec MOSFET in a TO2637 lead and TO247 4 leads. The concrete test setup is based on Littelfuse dynamic characterization platform, which is our evaluation board. And we use here the high side MOSFET to extract the body diode parameters and the low side MOSFET to extract the turn-on parameters and the turn-on parameters in a basic double pulse test. Reviewing some of the results obtained during this benchmark, we can see that if we follow the green curve here of the SMPD measurement, the Kelvin source eliminates the gate oscillation and the gate voltage disturbances. We see that the overshoots are reduced and small in comparison to the other packages. And if we look at the behavior of the body diode, we see that the recovery time, the reverse recovery time is shorter than the full packages, which basically increase the system efficiency by reducing the losses in the body diode. Now let's review the switching performance of the two devices sharing the same dies, so the SMPD and the TO247 free leads. Let's have a look at the switching energies first. If we look at the total switching energy, we see that in the case of the SMPD, it's reduced by 17%. And if we look now at the reverse recovery energy, the SMPD's performance shows an impressive 71% reduction in reverse recovery. And if we look at the switching time, we see logically the same effect. Looking at the total switching time first, it's reduced by 29% in the case of the SMPD. And here again, for the reverse recovery, the total switching time is reduced by 57%. So all these benchmarking results demonstrate the superior performance of the SMPD package and support our claim that this package is an excellent companion for SiC devices. As a final step of our demonstration, let's use a concrete example, namely a SiC-based 22 kilowatt DC charger. Considering this topology, especially focusing on the active front end in our case, and let's compare what happens if we would design this active front end using SiC half bridge in SMPD. So here taking the example of one of Littelfuse products, 1.2 kilovolt, 25 milliohm half bridge, SiC half bridge. Comparing this with the same design based on the chips, the same chips, especially in TO247 package free lead. If we calculate the number of components we need to meet the output power target just discussed, we see that we can achieve it with just 3 SMPDs as compared to 12 TO247. This translates into a much higher mounting effort for the through-hole discrete solution, not even mentioning the associated risks in terms of yield and quality of the build. We can see as well that the total PCB area needed is reduced by more than 50% when using the SMPD. That leaves room to build in more features or maybe reduce further the size of the housing. Also in terms of performance, comparing at device level, of course, the SMPD is worse due to the built-in isolation sheet, but it's a different story if we compare the resistant junction to heatsink. Here we see that the SMPD fares much better. And in fact, we can dissipate over 30% more power with a design based on SMPD. It's already time to conclude this presentation, so let's have a quick wrap up. The ISO plus SMPD package is a DCB-based isolated pick-and-place compatible package with excellent thermal performance and reduced commutation loop inductance. It can host simple power electronic building blocks, including extra functionalities like, for example, temperature sensors. And at the same time, it keeps the convenience of a discrete package from the point of view of automated manufacturing and compactness of PCB design. In that sense, SMPD brings key advantages to fully exploit the performance of silicon carbide chips. And by the way, it is not limited to SiC nor to a fixed catalog of devices. So please contact Littelfuse if you wish to discuss your needs for specific circuits and/or customization.